In the last class, we were exposed to the variety of MOSFETs as well as JFETs available to us, and we are now depicting these things symbolically, covering all the possible combinations of types of FETs, starting with JFETs, N channel, P channel. These are basically depletion mode devices, and then we have enhancement mode devices, okay, where there is no channel existing. Only after a threshold voltage is applied, the channel can come into existence. Okay. And then we have in this N channel and P channel. Then we have the channel already diffused into this. Okay. So, these are the depletion mode MOSFETs, which can be operated also in enhancement mode, but they are popularly called depletion type of MOSFETs. So, let us therefore use these active devices in a variety of applications. First and foremost, I would like to bring out the fact that any of these FETs one can use as a resistor, voltage dependent resistor. So, this controlled voltage dependent resistor effect of the FET is what we are now going to discuss in detail, because unlike the bipolar junction transistor, this is one active device which can also be used as a passive device, that is a controlled resistor. Okay. So, let us see how this FET, it could be JFET, enhancement type of MOSFET, or depletion type of MOSFET. I am just taking one type of FET here. Since the equations look identical, whether it is enhancement or depletion type, we can use the one particular type for illustrating any particular example. Now, we know that IDS, this is the drain, this is the source, and this is the gate. The IDS versus VDS, if you plot, it is going to be linear. As long as VDS is small. This we have understood, and we have understood also that this equation is simply governed by IDS equals 2K times VGS minus VT into VDS. So, please remember this linearity comes about because of this relationship. Okay. IDS is directly proportional to VDS, and the proportionality constant is 2K into VGS minus VT, which means that the resistance RDS, which we said is going to be quite useful for us, is nothing but VDS. See the difference. This is supposed to be VDS divided by IDS itself, okay, V by I, Ohm's law, and that is equal to 1 by 2K into VGS minus VT. This is valid then, as long as it does not really go to what? This nonlinear region. After a certain point, this goes to nonlinearity here. So, this resistance, linearity should not be disturbed by this nonlinearity. Similarly, it goes like this here. So, as long as that is not disturbed, as long as the deviation from the linearity is not much, that means around VDS equal to 0, any of these FETs can be straight away used as a controlled resistor. Okay. The slope being controlled by this VGS. Now, further modification. IDS actually speaking equals 2K into VGS minus VT into VDS, and that this nonlinearity we said is square law, VDS squared by 2. This is approximate, therefore, we will say this is exact. Now, suppose I want to use this as a good linear resistor in this region. This equation is valid, okay, for what? VDS less than VGS minus VT, less than or equal to. That is called the triode region. For VDS less than or equal to, until pinch off is reached, this is valid. That is, this is valid up to this point. Okay. And this voltage corresponds to VDS equals VGS minus VT. So, this. It is valid up to that. This equation is valid. After this point, that is for VDS greater than VGS minus VT, what is valid? That you can substitute VDS equal to VGS minus VT, and you will get it as K times VGS minus VT whole squared. Okay? That is what is valid. Now, in this region, can I therefore compensate for, okay, this nonlinearity? So, what we are now today going to discuss is to make it more linear, okay, by compensating for this nonlinearity. So, this can be done using circuit. Okay. What is responsible here is this VDS squared by 2. Okay. This is getting subtracted from this and is getting added here, because this VDS, okay, is positive here and VDS here is negative. So, and this remains negative throughout. Okay. So, the current increases here, the current gets saturated there because of this nonlinearity. Now, how to get rid of this? Suppose I make VGS equal to, I want to get this rid of this VDS. Okay. So, I will see, if I make VGS equal to VDS by 2 plus something, this VDS will multiply with VDS by 2 and cancel this. So, I will make VGS equal to VDS by 2 plus, let us say, VC by 2, some control voltage. This is off, right? This is an independent voltage, but I will make VGS equal to, okay, to compensate for nonlinearity. Make VGS equal to V. How we make this is to be seen. Make VGS equal to VDS by 2 plus VC by 2. VC is the control voltage. Normally, VGS is made equal to VC, right? Now, instead you make VGS equal to VDS by 2 plus VC by 2, right? Then what happens? Substitute VGS here. So, what do you get? This becomes 2K into, if you do this, 2K into VGS, VDS plus VC by 2 minus VT into VDS minus VDS squared by 2. Now, what happens here? This term cancels with this term exactly. VDS by 2 into VDS is VDS squared by 2 gets cancelled with that, and we are left with 2K into Vc by 2 minus Vt into VDS, which is perfectly linear as far as VDS is concerned. Now, what is the circuit that will give you VGS, which is VDS plus Vc by 2? A simple resistive attenuator. Okay? Let us see how it looks like. Okay? So, if I use here Vc, this is nothing but, what is this? This is VDS. This voltage is VDS. This is Vc. So, I put equal resistors R and R. This is anyway gate. Okay? This is not going to. So, if I put equal resistors R and R here, the voltage here at the gate, which is VGS, okay, because S is grounded, is going to be Vc plus VDS divided by 2. Is this point understood? This voltage is defined as VDS. This is Vc. So, at this point I can get VGS, that is, which is equal to Vc plus VDS. So, a simple circuit like this is going to get rid of this dominant nonlinearity. Okay? That means now it is enough if VDS is less than or equal to VGS minus VT. As long as that is true, this relationship is valid. Whereas in earlier situation, if wanted to approximate this, okay, then VDS should have been much less than VGS minus VT, right? Then only you can make this approximation of neglecting VDS squared by 2. That means you should have worked at a voltage because it is corresponding to a point which is much less than this point, farther into this region. Whereas because of this, now we can go all the way up to pinch off, okay, as long as you are in the triode region, as long as this equation is valid. Okay, this is perfectly linear. That means these things are becoming perfectly linear here, okay, for all the FET characteristics. Is this understood? This is an important concept of linearization of FET resistance, which you can use in your practical circuits, okay, wherever you want a controlled resistor. Let us see the application of controlled resistor. So, the same circuit is valid whether it is a JFET or a depletion type of MOSFET. I have illustrated it for what? Enhancement type of MOSFET. Okay. The nonlinearity occurring in all these things will be exactly same type, that is VDS squared by 2 type. Now, let us consider the circuits, okay, which are possible with these active devices. As we did in the case of bipolar junction transistor, first we will consider the basic inverter. So, I will consider now what you call as NMOS inverter. Okay. Just as an example, you could as well take PMOS inverter or CMOS inverter, but NMOS and PMOS inverters, okay, are looking almost exactly identical in their characteristics, right, except for the voltage bias difference. So, now for the time being I will put a resistor here. Just as we have been putting this voltage as VCC in the case of bipolar, because this is for biasing the collector base junction, we will call this VDD because we are connecting it to the drain. So, this is a single supply inverter. Now, consider this circuit, simple circuit. We have this as let us say positive, and here we are applying VGS, and this is the output voltage which is equal to VDS. This is the input voltage. Vi is equal to VGS is the input voltage, V naught equal to VDS is the output voltage. Now, call this resistance as RD. So, we would like to now know about the what is called transfer characteristic. What is it? Let us put this as IDS. Okay. So, basically we can write down the characteristic in the following manner, that VDD minus, this is DC I have put, okay. If I consider the instantaneous values, okay, I can consider it as IDS. This is the symbol we have been consistently adopting, right, instantaneous value, okay. It is varying, time varying, it will contain DC as well as AC, IDS into RD equal to VDS. VDD minus the drop here, which is IDS into RD, is the voltage which is VDS, which we will be calling as output voltage. Right, and we have VGS same as equal to VI. That means IDS equals, assuming that the transistor is in the current saturation region, IDS is equal to K times VGS minus VT whole squared. So, K times VGS minus VT whole square, which is equal to K times VI minus VT whole square. So, we are getting the relationship V naught as equal to, okay, VDD, a constant voltage, minus IDS, which is K times VI minus VT whole square into RT. This is what is called as the output versus input characteristic. If you therefore plot V naught versus VI, until VI becomes equal to VT, there is no IDS. Until VI becomes equal to VT, there is no IDS. IDS is 0, it is off. The effect is off until threshold voltage is reached. Current is 0. So, until VI equal to VDS, VT is reached, IDS is equal to 0. The transistor T is off. So, output is going to be at VDD. Output is going to be at VDD, because IDS is 0, T is off. At, let us say, Vi equal to Vt, the channel has got formulated and the current starts flowing, right. So, what will happen to the output voltage? It will start decreasing. Now, is the FET in the current saturation region or triode region? In this, here T is off. The question is, the voltage here VDS in this case, okay, is equal to VDD itself, okay, because V0 is equal to VDS. So, that is equal to VDD, that is the highest voltage possible, right. The current is starting from 0. Is the FET in the current saturation region or triode region is my question. Have you understood the question, right? Where is the transistor located? This voltage is the highest possible, okay. The current, the transistor enters current saturation region for all voltages VDS greater than VGS minus VT, okay. VGS in this case is Vi, that means for all voltages greater than Vi minus Vt, okay, the transistor is going to be in the current saturation region. Obviously, if at all I want this transistor to be in the current saturation region, this particular point at which ID is 0 and this is the highest should be the point where the transistor is in current saturation region, because that is the highest voltage VDS possible, VDD. So, the transistor at this point is in current saturation region. That means the equation that I have used is straight away valid. Why? Because V0 is equal to VDS is equal to VDD, okay, and therefore, T is in current saturation region, because VDD is greater than, okay, Vi minus Vt, okay. That is the assumption, okay. Then this particular thing therefore is going to, let us say, decrease in square law, right. That means something like a what? Something like square law means what? This is x squared, y is equal to x squared, that is a parabola, right. So, and up to what point will it go on like this until it enters triode region, because now this VDS is going on decreasing. Initially maybe VDD is greater than Vi minus Vt, okay. Now VDS is decreasing, not only that, Vi is increasing, okay, VDS is decreasing. So, there must be some point at which, what is that? What is that point? At which Vi minus Vt becomes equal to what? VDS, okay, or V0. VGS minus Vt equal to VDS is the point at which it enters triode region. VGS is equal to Vi, VDS equal to V0. So, corresponding to a point Vi minus Vt equal to V0, it will enter triode region. How do we know this? Because this is one curve, this is another curve. What is that? Vi minus Vt equal to V0 is a straight line, V I minus V t equal to V naught is a straight line. Okay. With put V naught equal to 0, there will be V I equal to V t. That means, at V I equal to V t, there is going to be an intercept here. Now, V I equal to this point. Okay. This is the point already, and I draw a line like this with 45 degrees, because if this scale is same as this scale, right, that will be a slope of 45 degrees, and that corresponds to V I equal to V I minus V t equal to V naught, this line, and this line will intersect this line. What is that line? This one, V naught equal to V d t minus k into V I minus V t whole square. That will intersect at a certain point. Thereafter, what happens? The FET is no longer in current saturation region, and it has entered the what? Triode region. That means, the equation that is valid now corresponds to V naught equals V d d minus, what is that equation that is valid? 2k, okay, into, okay, VGS is Vi minus Vt into VDS, which is V naught, okay, minus V naught squared by 2. Is this clear? This is the equation that is valid. That is 2k, this into Rd. IDS is going to be now 2k into VGS minus Vt, which is Vi minus Vt, into VDS, which is V naught, minus VDS squared by 2, which is V naught squared by 2, into Rd. So, this is the equation that is valid in this region. So, basically, the active region, the so called active region, where the FET is acting as an amplifier, is this region. Here the transistor is entering the triode region. Okay. Here the transistor is off. So, T is in the triode region. Here the transistor is in the current saturation region. So, this is the complete characteristic of an NMOS inverter. Okay. This also can be used as a digital gate. Okay. You have high as the input, output is going to be, that is, you have high as the input, output is going to be low. If Vi is equal to, let us say, this is the point VDD, output is going to be low. If the input is low, output is going to be high. So, this is a digital inverter, the famous NMOS inverter, which has been liberally used in all your what? VLSI circuits, because of its simplicity. Right? Now, only thing is, there is no such resistance that is used in these inverters in VLSI circuits, okay? Because the resistance takes up lot of what? Space. We know that MOSFET itself can be used as a resistor, just now we have studied. So, why not put MOSFET itself as a resistor, okay, instead of using a physical resistor there. Therefore, in digital inverters, all the resistors get replaced by MOS resistors, okay, MOSFETs acting as resistors. Okay. So, we will discuss that circuit later, but this circuit can also be used as an amplifier in this region. If you are operating, if you select your operating point anywhere in this region, this is going to be used as what is called as common source amplifier. So, NMOS inverter or common source amplifier. How? We can operate this anywhere in the region, let us say somewhere here. Okay. How do I operate it? I will make this as my VGSQ quiescent. Okay. This Vi is same as VGS. So, I will make this as VGS quiescent. I will apply a DC voltage, and then the signal will vary the VGS around this quiescent in such a manner the current is going to vary. Right? If this current varies, IDS varies, then the output voltage is going to vary. Therefore, the slope of this characteristic around this point, which is delta V naught divided by delta Vi, delta V naught divided by delta Vi, is called the gain of the amplifier. If you take the slope, it is negative here. The slope is negative, indicating that this common source amplifier is inverting, giving a phase shift of 180 degree, and the magnitude of this slope will give you the amplification factor. What is this? Therefore, that can be obtained by differentiating this equation. Right? So, please differentiate this equation, not this, because this is not the active region. So, the amplifier is set to enter the saturation region here. The amplifier is set to enter the saturation region, where the FET is entering the triode region. The amplifier again goes to the limit here, where the FET is in off state. These are the two boundaries within which you have to operate the FET in order to keep it as an active device. So, let us now obtain delta V naught by delta Vi for this is nothing but, please differentiate that, what do you get? Nothing here. So, minus minus 2k into Vi minus Vt into Rd. Right? So, this is nothing but the gain of this. Right? This is also written as minus. What is this factor? So, this is nothing but, after all, this is the IDS. This factor is nothing but IDS. So, because this is really speaking VDD minus IDS RD. So, if I differentiate this, actually speaking, you should get minus RD into delta IDS by delta Vi, right? Because RD is a constant. Only thing I can differentiate here with respect to Vi is IDS. So, delta IDS by delta Vi. What is delta Vi? Is same as delta VGS. Vi is same as VGS. So, this delta IDS by delta VGS is called output current variation for an input voltage variation. It is called transconductance. Its magnitude is conductance. It is from input to output that the change has occurred. For an input voltage variation, what the current variation at the output is. So, this is called the transconductance. So, the gain, therefore, this is also indicated by GM. So, this factor is called transconductance. So, this is equal to minus RD into GM. So, please remember that the same expression has been obtained in the case of bipolar junction transistor there also the gain was minus GM into RC. In the case of FET also the gain is minus GM into RD, and therefore, these are all exactly identical in their definitions. Okay. So, you should therefore know how one should obtain GM. So, the value of GM is nothing but minus not minus 2K into what? VGS minus VT. What is VGS minus VT? This can be written as 2K. VGS minus VT is root of IDS, right, cos divided by K. So, this is 2K into root of, okay, IDS by K. So, this is nothing but 2 root of K into. Is this clear? Because this IDS is nothing but K times VGS minus VT. This has to be evaluated at a certain operating point, okay, at VGS Q, right, that is the slope. So, IDS is equal to K times VGS Q minus VT whole squared. So, VGS Q, okay, minus VT is nothing but root of IDS by K. So, you substitute this. This is the value of, therefore, if you know the value of K and operating current, right, 2 root K into IDS will give you the value of GM. For FETs of similar dimension compared to the BJT, the value of GM is typically 1 order of magnitude less than that of corresponding bipolar junction transistor. For example, bipolar junction transistor at 1 milliampere, okay, if it has 40 millisiemens as GM, okay, then corresponding GM for the FET is going to be about 4 millisiemens. Okay. So, this is why if it is an amplifier that you are designing, it is advantageous to go for bipolar junction transistors rather than field effect transistors, because for the same dimension it is going to offer an order of magnitude better GM transconductance, okay, and therefore, it is better to go for bipolar junction transistor. So, let us now consider what is meant by distortion, which we had already discussed in the case of bipolar junction transistor amplifiers. If you consider that Vi is Vp sin omega t, this is sine wave. Right? We will now have V naught equal to Vdd minus K times Vp. Now, we should say Vi, if we make Vp sin omega t, we have a problem. We should have this superimposed over VGSQ, so that, okay, there is a quiescent point, okay, so that this voltage can go to positive and negative on around this point, okay. It can increase above VGSQ or decrease. So, we have Vi is equal to VGSQ plus Vp sin omega t, and therefore, Vdd minus K times Vp sin omega t, okay, plus VGSQ DC voltage bias, okay, minus Vt whole square. So, what do you get here? Vdd minus, we will now couple this on like this. This is nothing but VGS, okay, time varying VGS, but this is VGSQ DC minus this is another DC. So, VGSQ minus Vt, okay, is a DC. VGSQ has to be necessarily, okay, greater than Vt, right, in order to locate it in the active region. So, this is a positive quantity, right. VGSQ minus Vt is a positive quantity for this n channel device. Okay. So, this therefore can be put as a constant. Okay. So, we have this k times square this Vp squared sin squared omega t, okay, plus Vgsq minus Vt whole square, okay, plus what? 2 Vp sin omega t into Vgsq minus Vt. So, this whole thing into Rd. So, that is the output voltage. Now, let us see V naught is therefore going to be equal to VDD, which is a DC, okay, minus K times Vgsq minus Vt whole squared. What is this? This whole thing, because this is VDD minus K times, okay, Vgsq minus Vt whole squared, which is nothing but IDSQ, okay, this into Rd. So, strictly speaking, this whole thing is nothing but what is called as VDSQ, quiescent operating point of the FET, VDD minus K times Vgsq minus Vt whole squared into Id is nothing but IDSQ into Rd, which is VDSQ, DC voltage, right. So, that minus, okay, let us take the useful component here, K times Rd times, okay, 2 Vp, okay, sin omega t, which is the linear term, because we had applied only sin omega t, we would like this to be amplified and appear as a sin omega t term. Okay. So, this is the wanted component sin omega t into what? Vgsq minus Vt, right. So, that into Rd we have already taken into account, minus unwanted component. This is what is causing distortion. This is called the nonlinear term in our FET amplifier. Okay. So, we have this as K times Vp squared into Rd, okay, sin squared omega t. So, this is the nonlinear term. This is the linear term. You notice this, this is nothing but 2k into Vgsq minus Vt. What is that? 2k into Vgsq minus Vt is nothing but Gm, if you look back. Okay. So, this is nothing but 2k into Vgsq minus Vt, which is nothing but what we have already defined as Gm. Okay. So, we will replace this. So, we have already defined Gm into Rd, okay, is the gain, that into original input signal, which is Vp sin omega t, with a minus sign indicating there is an inversion, right. Next we have k minus k times Vp squared Rd squared sin squared omega t. Sin squared omega t can be expanded as what? 1 minus what? Cos 2 omega t by 2. So, you can see that this nonlinear term is contributing to a second harmonic distortion. So, predominantly in a field effect transistor circuit, you do not have other higher harmonics, okay, but they are predominantly second harmonic components which are present, causing distortion. And the extent of second harmonic you can learn by how? By seeing that there is a DC term caused by the same thing. The amplitude of the second harmonic is the same as the DC term which comes over and above the quiescent voltage. Let us say before you apply the input signal, there is a quiescent voltage which is called VDSQ. Measure this using a DC meter, then apply a sine wave and measure the shift in the DC output. That shift in the DC output will give you the amplitude of second harmonic. Okay? This is the technique I advise you to use even for measuring the distortion in the case of a bipolar junction transistor amplifier. Right? So, you can quickly measure the extent of this experimentally, okay, by finding out the shift in DC component DC, which is minus k Vp squared Rd by 2. Okay. So, this is something that you can in an experiment do very easily and find out what the second harmonic distortion is. If you are told that keep the amplifier second harmonic distortion less than 1%, okay, then this, okay, divided by this has to be kept, okay, less than what? 1%. Okay. This divided by this, okay, should be 1 over 100, 0.01. So, this is something that you can always do in design. Suppose you are asked to design a FET amplifier for an output distortion less than 1%, then you can also find out what should be the value of Vp, okay, what should be the limiting value of Vp to retain the distortion at less than 1%, because this is Vp squared, and if you divide it by this, okay, 1 Vp will still be there. The distortion obviously depends upon Vp. Okay. So, it will tell you the magnitude of Vp that should be constrained in order to keep the distortion at a value less than 1%. Okay. So, this part of the design is important in restricting the design, this thing, what is that, inputs to specific values. So, what is it? We can just see k Vp squared into Rd by 2 divided by Rd Gm into Vp. Okay. So, actually Gm itself is defined as 2k into Vgsq minus Vt, right. So, you can therefore get the extent of distortion, okay, using this, like we measured the input signal in terms of Vt in the case of bipolar junction transistor. Here you are going to do it using this k, right, the parameter associated with this. So, please see this Gm is really speaking equal to what? 2k into Vgsq minus Vt. So, k gets cancelled with this. Okay. So, distortion is really Vp divided by 4 times, okay, Vgsq minus Vt. If this is therefore to be kept at much less than 1%, that means 1 over 100, then you can find out what Vp should be. Vp should be much less than 4 times Vgsq minus Vt divided by 100. So, let us take Vt is 1 volt you take, Vgsq is, let us say, 2 volts. So, 2 minus 1 volt, 1 volt by 25, 1 by 25 volts, okay, which is 1000 by 25, or it should be kept at much less than 40 millivolts, or much less than 40 millivolts means typically of the order of 4 millivolts or so. Okay. So, this is a classic example as to how you should restrict the distortion. Okay. So, we will consider the other amplifiers in the next class.